So, after the specification sections, we can continue planning the device, and that is the purpose of this brief video on this idea. We have in mind inventing an RS latch that we know now very well how it works. So now the next objective is how to design an RS latch from logic gates to make, a kind of a continuation of content continuation from the one delivered in chapter 1 based on combinational circuits, okay? This is what you know. So now from these combinational circuits developed in previous projects, now the purpose is to use them in some way to invent this new circuit, inventing an internal architecture. So in the end, from this planning, we have in mind obtaining a circuit, whatever it is. For example, this typical one based on NOR gates. So how to get that kind of circuit? So hi, let me explain you how to develop this circuit before planning it a little bit, because in the other video we saw the way it works, and it worked like this. You have the symbol and you have the function table. That is the way we have to explain how the circuit is working. You have two input signals to order saving ones and saving zeros. So in the future, if you do nothing like this, you keep the value. If you click set, you save a 1. If you click reset, you save a 0. And if you click by any chance the two control inputs at the same time, nothing happens, or whatever, it's not defined. That's the way. No interest, okay? We have no interest on this input. This is the operation set, and this means save a 1, okay, and 0 means reset, save 0 at the output of the chip. So that is what we like now to invent, considering concepts and ideas from chapter 1, because this is what we have in mind now at this level of the course, at this stage, okay, in the course. We know how to invent circuits based on logic gates by several methods. Is that going to be possible now? Imagining that this circuit, it's perhaps a combinational circuit, can we do that? Well, perhaps we can do that. Let's try. So instead of a function table, imagine that now you have here a truth table, okay? And we know that we do that simply organizing the same inputs as in this way, with a double bar. So you consider all the combinations the same way, and you say that thing, if you like to set 1, if you like to reset 0. This may be a don't care situation. You are not interested in what happens when you have 1, 1. So this may be a kind of incomplete function. You have no interest on this combination. But here you have a big problem, you see, because when 0, 0, you like to keep the previous value, but the previous value may be very well whatever output, 0, 1. So what are you going to do here? 0 or 1, you see? So that is perhaps why you can solve that this way. This is impossible, you see? This in the previous chapter, a given single combination of inputs, it's only for generating a single value. It is a max term or a min term. So that thing is impossible. But here is what exactly you are pretending, to keep the current value. If it is a 1, let it be that way in the future. And if it is 0, let's keep it. So that means that we cannot solve this new chip as another example of designing logic functions, as if you were designing combinational circuits in chapter 1. So what is that we can do? Perhaps we have to squeeze our mind and to get something else. For example, if this is the idea that all the time we have in mind, inventing something, this is the R, the S, and the Q. We do that all the time. So this is the chip RS latch. So very well. If the only thing, now we can do that in many ways, but if the only thing that is available to you, because we came from chapter 1, perhaps is, yes, we must think in a combinational circuit, you see? A combinational circuit. Okay, we must, because there is the only tool available. So this is why you may imagine a component inside that is a combinational circuit. So a circuit that is from chapter 1, a typical combinational circuit. So let's do it like this. You may like to have R, S, and make that connection. Okay, it's all right. And then, well, let me show you this. I will make here the use of a buffer to make the things clear. And what I'm going to do is to use another color now to represent, you may call that Q, very well. So what I'm going to do is this new strategy here. Look at this. I will use the output to do that kind of, you see, feedback loop. So now I be able to, you see, I can name it Q, because it's a signal, so I can name this signal Q, so I've got the Q here, right? And if you like it in the same colors, it make no difference. So you have the Q, the R and S, but you see now you have here this internal, okay, this internal wire that is a kind of feedback. Okay, so why for? Well, and perhaps here there is an inconsistency, so we have here the possibility to use the same Q, just naming it like this, you see, just to make a difference. So this is Q and this is Q plus. So in some way, Q now, you see, whatever you are inventing internally doesn't matter. Now, you see the Q plus is not that simple. It is a function of R and S and Q, all right? So that is the point. Here you are, the internal state or value of the variable, and this is external control signals. That makes sense, okay? Well, it will make sense if it is possible to go to the end, because that's not enough. Now we have to continue inventing what goes here. So if we have to invent the internal architecture of this combinational circuit connected in this capricious way, well, you know what we have to do. You see, as usual, we have to take the block and invent the truth table immediately, because if not, if we don't do that, we cannot go anywhere. So, because remember that in the end, a function is going to be just a circuit. So the truth table, right? Now, yes, let's try to develop the truth table. Is that possible? Well, we have here some room to do the same, a similar table like that one here that was impossible, but now let's imagine that R, S, and Q. And perhaps you may like to make that separation. You see, why not? Because those inputs are different. Those are external inputs, and that one is a kind of an internal wire. So, but doesn't matter, as if we think about the combinational circuit, what goes next is simply the writing of all the possible combinations as usual, you see? It is like if we go back to the chapter 1, so 0, 1, 2, 3, 4, 5, you see, 6 and 7, something like this. But now you see the position of the variables, the order that we have given allows us to subdivide the table in 4 sections in order to establish the output. And for example, If well, and this may be q plus if you like, no problem. So you see, just to make a difference, yeah, it's the same wire, you know, it's that kind of thing that is complicated even to think about it, but doesn't matter because, you know, uh, it is not that, well, it's just a formality to do that this way, to make it simpler, to visualize what happens. So look at this. If you are applying 1, 1, well, you are not interested really in the value. You see, it's a kind of this x. So very well, you can do that here. The same thing. Not don't care. It's a kind of a don't care, and this makes a kind of a incomplete. This is the incomplete function. Okay. Now what? Well, there is something very clear. If you like to reset, you see, this is what we call reset. So what you like is a 0. For any combination 4 or 5, doesn't matter if the system already have a 0. If you are ordering a 0, you save a 0. If you are ordering, if the system now currently is saving a 1, you have to change that situation. You have to flip the output to 0. And the same here, but with a 1. Okay? You like to save a 1. Change the internal state from 0 to 1 or keep the internal state from 1 to 1. And then the point is that now you have possibilities. So this is the set. And here you are something that is very good because you see 0, 0. If you keep the 0, what you want is exactly to keep the 0 that way. This is, you see, keep the 0. Because this is what you like to do. And if you have 0, 0, but the system is saving a 1 now, what you like to do is to save, to keep the 1. So that is perfect, you see? This is the idea of keeping the current state. Keep the current value. So this is the table, okay? And now, naturally, if you already have the table, you can invent the second. And for example, now you are entitled to use the max terms, min terms, product or sums or whatever. For example, Q plus, attending to this table, may be very well the sum of some min terms. The min term 1, for example, the min term 2, and the min term 3, that way. And then if you like to consider in the formula as well the don't care, you may add or the sum of the don't care terms 6 and 7. That's you know, that means that don't care the don't care terms can be written like this. Or why not, Q plus is also the product of the max terms that are not min terms as usual. So the 0 and then the 4 and the 5 and you know, and the product of don't care terms 6 and 7. That's a formula very well valid for writing the truth table. And now is when you can do what you want. Translate this sum of min terms, discarding the don't care terms, and you can invent the min terms as a second. Or why not? You can go and run Minilog, for example, to get let's see a sum of products, for example. If you do that, Q plus becomes, let me see, R, it is R naught Q or R naught S. That is what you get, a sum of products. So now you have a second, and that's the end of the planning because the second is looking like this. You have this is R, this is the literal R, R naught S, S naught, and this is the input Q, Q, and Q naught. And now you take this term, you see, R naught and Q, and then there is the other one, the same R naught, but now with S this way. So this is the product and another product, and that's the final OR. So this is the function Q plus. That's a perfectly well circuit for this application, 1-bit memory cell, right? But some people like another one, like this circuit, the one that is generated when you, for example, you know, because it's an equation, you can modify the equation the way you like, and for if you have another equation, you have another circuit. So you may like generate a common factor R naught, Q or S, something like this, and then if you like, you can not 2 times in some way to generate a circuit that is based only on NAND or not. So if you do that, okay, you get something like this: R not not, or Q or S not, and then a final general not, something like this, which means that now your circuit, maybe this is, you know, R simply, so you have R, look at this, you have R, and now you may imagine that here is the Q, or okay, so you can take the Q like this as the input of another NOR, and this is S, okay, so this is S or Q not, and exactly S or Q naught is what you like to OR with R. So like this, you take this wire up here as another input, and now you have what you want. It is Q plus if you like, okay? Something like this. So this is the typical 1-bit memory cell that is represented in many books and literature, and it is perhaps implemented also as a chip, perhaps not using NOR but using NAND, but it's the same idea, okay? So now what goes next is simply transferring this schema, for example, into, or this equation, doesn't matter, you like to transfer that into a BHDL representation, a file, and then run the development stage and the testing stage to see by means of a test bench whether the circuit works as expected or not, okay? So that's the end of the planning.